Alright guys, just so you know, there's some machinery right outside my house. So if you hear it in this video, it's just that, alright? I don't think the mic should pick it up, but yeah. Number 2, we have our good old friend Ansel, who's designing a racing track for a local bicycle club. The following diagram shows an incomplete portion of the track. And so clearly the incomplete portion is something that goes like this in order to connect the two tracks, right? And so our good old friend Ansel wants to design the track such that the inner edge is a smooth curve from point A to B, which is what I put earlier, and the other edge is a smooth curve from point C to D. The distance between point A and B is 90 meters. Okay, so these 90 meters are this whole thing right here, all right? As this arrow is telling us. So, why didn't I just do that? Well, you want to first get the context of the problem, but also make sure that all the numbers they give you are actually in your diagram, and if they're not, draw them in. And so right now, everything that they told us is in our diagram. Nice. And to create a smooth curve, Ansel first walks to M, which is, ding ding ding, keyword, midpoint of AB. So M for midpoint, M is the midpoint of AB, and to write down the length of BM. Alright guys, this is pretty standard stuff, so if this is the midpoint, that means this is the middle between both A and B. And so that means that this distance that I'm putting in red is the same as this distance that I'm putting in red. And so the length of BM is one of the red lines right here, right? So this is the length of BM. And so, okay, if you have two red lines that are worth the same, right, in distance, right, and the whole thing is 90, that means for finding BM, you just need to do 90 divided by 2 gives you 45. Don't forget your units, 45 meters. So that's some pretty standard stuff. You just need to understand what they mean by midpoint. That is part A. Then they keep telling us a bunch of other stuff. That Ansel then walks 32 meters in a direction perpendicular to AB to, to get from point M to point E. And so this would be point E right here. So that means that, okay, we just found out that this is 45. And then this right here from M to E is 32. Okay, that is what we know right now. Point E, they also tell us, is the center of a circle whose arc will form the smooth curve between points A and B on the track, as shown in the following diagram. So these lines that I'm now putting in, I don't know, whatever, purple, right? So from here to here and here to here is sort of what I drew earlier, okay? And what the problem is telling you, like, okay, to generate this arc, technically this comes from a full circle, right? Mathematically. And the center of that circle is right here on point E. Okay? And so in order to generate the arc, our good friend Ansel, first of all, has a lot of time on their hands. And second of all, is dedicated to making this sort of circle. Okay, and so this sort of circle is the one I'm talking about. That is why Ansel is doing what he's doing. And yeah, that is the current context. And so for part B, notice we merely have something that is part BI and part B double I. The cool thing about the IB, if anything, is that whenever you have an exercise with two parts to it, they are completely and utterly related to each other. So I know a lot of times they say, como, what you need from part B is what you use from part A, but not always. So it's a hint, but not always. Be careful. Okay, whenever you have like part one, part two, in my experience, they are always related to each other. So that's the first hint that I can give you guys. Whatever you get on part BI is what we need for part B double I. That being said, part BI, we need to find the length of BE. And so the length of BE is this right here. Now, I know this diagram can be a little bit overwhelming. There's like a track and there's like technically there's like a circle going around and there's like these two arcs and like a bunch of different stuff. I know it can get a little bit confusing, but whenever they ask for the length of something, just focus on that something, okay? of all your diagram, you're suddenly going to realize, once you concentrate enough, that you just need to focus on this length, and this length is associated to this triangle. So suddenly, part BI is much easier because you are only looking at this. You're only looking at B, at E, and at M. And you're going to plug in all the information you know. On the one hand, this is 45 for distance. On the other hand, this is 32. And the length BE is what you're trying to find. Do you know anything else? Yes, you do. Here they tell us, and I didn't point it out earlier, in case you might have noticed it, is that Ansel then walks these 32 meters, which is the 32 I put right here, in a direction perpendicular to AB. So if it moves in a direction that is perpendicular, that means bada bim, bada boom, ladies and gentlemen, we've got a 90-degree angle right there. And this is a mathematical rule, okay? The word perpendicular, so you usually have what we call, wait, hold up, that is not an E, okay. This is probably not an R either. So perpendicular, so you usually have either parallel or perpendicular, see? So we talk about parallel lines, parallel slopes, perpendicular lines, perpendicular slopes. It's pretty much a synonym. And so parallel lines, it's probably a little more familiar. It's two lines that never touch. But why do they never touch? They never touch because they have the same slope. So if this is line 1 and this is line 2, for parallel lines, slope 1 equals slope 2. Then that way, for example, the slope of this first one that I'm putting in green, like this is how much it advances per x. Well, for line 2, it's exactly the same. And so because they grow in the same manner means that they will never touch. For perpendicular lines, it's a little bit different. It's like they cross each other, but it's at such a way that always for line 1 and line 2, you will have that the first slope times the second slope is -1. And so technically from here, the first slope is going to equal the second one flipped times a negative, right? It's a mathematical rule. So for perpendicular slopes, you can flip it and multiply by -1. Now, why am I saying all of this? Because technically, because they are the negative reciprocal, just trust me on this, you will always have 90-degree angles in all these four sides. As long as they're perpendicular, you gotta be thinking in 90 degrees. All right, so perpendicular, 90 degrees. Perpendicular, 90 degrees. Perpendicular, 90 degrees. All right, so all of that blah blah was just to tell you like this small word this small word perpendicular is telling you that this is 90 degrees. And now, bada bim bada boom, a bunch of different tools show up. And so, ladies and gentlemen, if you're trying to find the missing side on a right-angled triangle, you should be thinking in the famous Pythagoras theorem. Now, Pythagoras theorem, you can only use it if you have a 90-degree angle on a triangle. So whenever you have Pythagorean theorem, we're going to call this A, we're going to call this B, and we're going to call this C. Okay? Now notice, C is like the long one. C is the one that is alone. And so in the formula, a squared plus b squared equals c squared, all that really matters is that the c that you pick has to be the one that is on the hypotenuse, okay, the long part. C has to be on the hypotenuse, has to be on the long part. Technically, you can mess up and call A B or B A, and it wouldn't really matter because it's on the same side of the equation. It's just going to be flipped, right? I mean, what's the difference between this and this? But there is a big difference if you confuse your C. So all I'm trying to tell you to really keep in mind for the Pythagoras theorem is that C has to be the hypotenuse, which is very fancy math language for saying the long one. Okay, so the long one is your hypotenuse. How else can you remember it? It's the one that is opposite to the 90 degrees. So for example, this 90 degree, its opposite is side C. This 90 degree, its opposite is X. Ah, so now I can say, okay, whatever, 45 squared plus 32 squared equals x squared, right? X being the length of BE, And so from here, let me just pull out my trusty rusty calculator. Here you can say, well, if you want to skip a bunch of steps and look really, really cool, you can actually do the square roots right away. And so this goes away with this. You end up with x equals the square roots of this. So that will be the length of BE. And if I plug all of that in just to show you, so you guys trust me, because I am, after all, just a guy on the internet. You usually don't want to trust guys on the internet. You can put all of this into your calculator and wablam. X equals this. So X equals 55.2177. Okay? If you want to do significant figures, you would be counting 1, 2, 3, and ask yourself, do you round it up or keep it the same? Clearly, you keep it the same. So significant figures, if you want, you can leave it as 55.2. So the length of BE is going to be 55.2. That is for part BI. And now you're going to find angle BEM. How do I know it's an angle? I know it's an angle because when they ask it like this, with a little hat, it's saying find angle E that is generated by sides B and M. Because angle E, technically, you guys, angle E can be so many things. I mean, angle E can be this guy. Angle E can be this guy. Angle E could even be this guy. Okay, so how do you know which is which? Well, they give you the B and the M, right? So, and because we're in this context of the triangle and everything, it just makes a lot of sense that you will be saying, okay, so I'm looking for the angle that is enclosed by B, enclosed by M, the one's next to it. Okay, I'm looking for this angle, see? Which is this angle here. And so now, well, this triangle now has more information. You know that this is 55.2, right? So you know that this is 55.2. And you need to find angle BEM, which is the guy that I put in, you know, coffee color, in brown, whatever, okay? Yeah, so this is what we're trying to find for part B double I. This is what we're trying to find for BEM, see? From here, there's a couple of tools, okay? And now I wanted to take a moment to talk about the ideal approach, in my opinion, for, whoops, you might have seen secret information there. The correct approach that I suggest for trigonometry, okay? And so clearly from here, because you're in a triangle and you're trying to find angles and sides and a bunch of stuff, we're talking about trigonometry. So the approach that I suggest for trigonometry is the conservative approach. Okay, what's always going to work is first try sine rule and then try cosine rule. Okay, this is the order I want you to employ. Now, if you want to do like a shortcut, okay, so I'm going to put trig shortcut. A trig shortcut is to consider the SOHCAHTOA. Okay, and here I'm talking about, better side I should say sine, cosine, tangent, SOHCAHTOA. Okay, so trig shortcuts would be this, right? But for this, you need a right angled triangle. So that means we're talking about a 90 degrees going around, see? So whenever you have a right angled triangle with 90 degrees, you can use SOHCAHTOA. Now, this is a shortcut. What I suggest, which is the more conservative approach, is using sine rule and cosine rule. What's the intuition of this? Sine rule works in pairs, while cosine rule is basically like one missing side or angle. So whenever you have only one missing side or only one missing angle, or better said, you're looking for just one missing side or one missing angle, cosine rule is pretty good. Okay? Now, I know that one missing angle sounds kind of weird because, oh, you have 2 out of 3, you can get the last one easily. Really, the cosine rule, you know what? I'm just going to show you. Okay, I'm just going to show you. You got to get familiar with the formula booklet. So here, if I go to cosine rule, as you can see, there's 2 versions of it, right? You have the version on the left, you have the version on the right. And so the version on the left, it has a small c that's alone. See? The one on the right has a big C that's alone. There's big letters, there's small letters. What the heck is going on? If you pop out a triangle, okay, The big letter, for example, angle A, big A, is associated to little a. Angle big B is associated to little b. And angle big C is associated to little c. Okay? So in other words, little letter is a side, big letter is an angle. And so for cosine rule, if you're looking for one missing side and you have the other two sides, right? And you have the angle of your missing side, you can use cosine rule. So again, if you're looking for one side, you have the other two ones, and you have the angle associated to that side, you can use cosine rule. While the other version is, yo, I'm looking for one angle and I have all the sides. All right, so that is what I tried to express earlier. So it's not really that you're looking for just one side or angle, but maybe now it makes a little bit more sense. See, while the sine rule clearly works in pairs, because you have two equal signs, you can just look at it like this, okay? Now, to leave this a little bit more intuitive, okay, you have little letters on top, big letters on the bottom. So all this is really saying is that your side 1 divided by sine angle 1 equals your side 2 divided by sine angle 2. So as long as you have like two pairs, right, and maybe you're missing just one of these, so let's say you're missing only sine angle, well, you can get sine angle alone, okay? So you got to think about it in pairs for sine rule. Cosine rule is a little bit weirder, so that's why I suggest doing it next. And that is the approach I will say. See? So a trick back to reality, basically. A trick shortcut, okay, is that whenever you have a right angle triangle, you can consider sine, cosine, tangent. Now, sine, cosine, tangent, we remember it as so and ka and toa. And if you never learned it, well, you can learn it now. So soka toa, for example, you have a triangle like this, okay? I'm actually going to redraw the triangle that we have. And so the triangle that we have, we said that this is M, this is E, this is 32. So it's the same, just flipped, okay? This is 45, and this is 55.2. And we need to find this angle here, okay? So I just redrew it to make it a little bit more friendly. This is the angle we're trying to find. Whenever you have a right angled triangle, you can use soka toa. And so the idea is the following. So is for opposite over hypotenuse. And this is a reference to sides. So if you have the sides opposite over hypotenuse, you can use this. If you have the sides for ka, it's going to be adjacent over hypotenuse. Adjacent is right next to. So if you have this, you can use ka. And for toa, you have opposite over adjacent. If you have these, you can use tangent, right? Now, all of this is in respects to an angle. So for example, for this angle here, right, we have to consider like what we can use for this angle, right? And so technically, if you're thinking about the perspective of this angle, one approach that you can employ, okay, one approach that you can employ is that you say, okay, we're gonna call this theta, just to like represent an angle. Okay, so if you go ahead and call that theta, you can say, you can actually use all of these. So you can say that sine theta, okay, sine theta would be opposite over hypotenuse. So the opposite would be 45 because it's on the other end. The hypotenuse is always going to be the long side, so the 55.2. So you can say opposite over hypotenuse, right? And from here to get this theta alone that's in here, you need to get rid of the sine. And so what's the opposite of sine? Sine inverse. So if you do sine inverse to both sides, which is the same as like dividing by 2, okay? It's just something you need to do to both sides. You can do sine inverse to the other side. You end up with only theta, right? So only theta, which is the angle you're looking for, is sine inverse of all of this. Make sure that your calculator is in the mode degrees. So again, I pressed mode, went to degrees, and here, so sine inverse of this, gives me this value here. So angle BEM is 54.60. All right. 54.60, I can just leave it as 54.6. All right. So this is going to be my angle theta. and this is going to be for part B double I. All right. Now, you can just skip ahead and go to part C. Now I'm going to show how you can do it with sine rule. Okay. So to do it with sine rule or any other of the ka or to or whatever, see, for example, for ka, for cosine, you would say cosine adjacent hypotenuse. So adjacent hypotenuse, adjacent is right next to. So right next to is 32. And you might be thinking, isn't it 55.2 right next to? And I would say, yes, it is right next to it. But before that, it's the hypotenuse. And so adjacent basically is the one next to it that is not the hypotenuse. So for cosine, you can set it up as cosine theta equals adjacent over hypotenuse would be 32 over 55.2. So from here, you end up with cosine inverse of 32 divided by 55.2 if you follow the same process. And lo and behold, it should end up being the same thing because we're trusting math, we're trusting the process. It's pretty much the same thing, right? So because of decimals, it's just a little bit different. But with three significant figures, 1, 2, 3, you round up this 5, you end up with 54.6, okay? And if you want to do tangent, which is usually the weirdest one, so if you want to do tangent, you are ignoring for tangent, you would be ignoring the hypotenuse. You only care about opposite and adjacent. So I'm going to do that in blue. Okay, so opposite would be this. Adjacent would be this. You would be saying tangent of theta equals opposite over adjacent. Okay, so tan inverse of this would be 45 over 32. And this should also give me 54.6. 45 divided by 32. The same idea. So you count 1, 2, 3, round it up or keep it the same, you round it up. 54.6. So that is showing how to do like a quick shortcut with SOHCAHTOA. Whenever you have a right angle triangle, it works. Now, as you've seen in my videos, I always suggest, I don't know, SOHCAHTOA, I know it's confusing for a lot of people. The whole thing about using tan inverse in order to get rid of the angle, like that can get fishy sometimes, see? And so I usually suggest sine rule. And so for sine rule, you'll be thinking in pairs. And so let me just erase a bunch of this information. And actually, let me do it from here. Okay, let me do it from here. And so from here, you would be thinking in pairs. And so technically, do you have a complete pair? Yes. You have this 90 with this side. And so immediately, you can already say that you have the side 55.2 divided by sine 90. Okay? And all of this is going to equal, well, you want to find this angle associated to that side. So all of this is going to equal 45 divided by sine that you're trying to find. We're going to call it sine theta. Okay, whatever. This is now going to be theta. So this is theta. You're trying to find sine theta. And so from here, well, how do you solve it? You end up doing a cross multiplication whenever you have two fractions equaling each other. So you end up with 45 times sine 90 equals 55.2 times sine theta. Okay? And so from here, in order to keep getting theta alone, you can do divide by 55.2, divide by 55.2. So that means that this goes away with this. In order to keep getting sine theta alone, you can do sine inverse once again. So sine inverse of all of this and sine inverse of all of this. So that means that with the sine inverse, this goes away with this, and boom, you end up with only theta. So theta is going to equal all of that, which yes looks nasty, but trust the process, it's going to work out. I'm going to go ahead and do sine inverse and then put a fraction. 45 times sine 90 divided by 55.2, close parentheses, there it is, 54.6. Theta equals 54.6. All right, that is basically just like a million ways to solve it. I'm sure one of them comes to mind. I'm not going to show cosine rule because I am strict to my law that you first try sine rule, and if that doesn't work, go to cosine rule. In this case, I do not need to reach cosine rule. I could have shown it, but I'm not going to show it. Because what I suggest you guys is go to sine rule. If that doesn't work, go to cosine rule. In this exercise, sine rule worked. I'm not going to show cosine. If you want to look at a cosine example, you can look up a lot of my videos. Just put the buzzword cosine rule. That being said, on the one hand, sorry for making such a long video, but on the other hand, I'm sure someone out there really appreciated what I just did, so this one's for you. I hope it helped. Now, for part C, you need to find the length of arc AB. And so here there's a lot of stuff that can sort of like jump out at us, okay? On the first hand, they use the word hence, which sounds very fancy. It is raining, hence I took an umbrella. I was hungry, hence I cooked some fried eggs with salt and pepper. Alright, anyways, so hence, besides being a little bit fancy, is also like, it's like therefore, okay? And so, this is a big hint because, everything I did in part B, because they put this hence, means that it's super useful for part C. And so this is a big, big hint that, okay, part B was extremely relevant for part C. Whatever I did in part B, I needed to find the length of arc AB. And so this is another big buzzword. What is an arc? So once you play around with your formula booklet enough and you study with it right next to you, down here you have length of arc, area of sector. Now an arc comes a little bit from arcway, okay? And so an arcway is like you have two pillars, and the arcway is this part here, okay? This would be your arcway, all right? And so in this exercise, the arc, as you can see, is this guy here. Now, technically there's two arcs, right? There's the arc that's like on the bottom, see? And there's the arc that's on top. In this case, they want you to find arc AB, the one at the bottom, the one that I just put in black, okay? So how can you find the length of arc AB? This is why the formula booklet exists. You read the word arc, you jump over here, and you say, yeah, I know there's a formula for length of the arc. Maybe I forgot how it was. You're not supposed to know it by memory, but you are supposed to identify arc equals formula booklet equals find it. And so you find it, and you stare at it, and it says length equals theta divided by 360 times 2 pi r. What the heck is theta? What the heck is r? What the heck is pi? So theta, they tell us, is the angle measured in degrees. Okay, so it's just like a normal sort of way to call an angle. You also have radians, but for the IBAISL, I'm pretty sure we don't care about radians, all right? And they also tell you that r is the radius. And so radius for a circle would be from here to here, this is radius, okay? A radius plus a radius gives you the diameter, okay? And if you put all of this in a diagram, it looks like a Pokeball. Anyways, so you have the circle, this is radius, radius plus radius gives you diameter. So diameter is 2r, okay? Or technically it would be r plus r, you end up with 2r, okay? Enough blah blah. And so the length of the arc that you're trying to find is AB, right? And so the angle, right, the angle that you need to find the length of the arc, right, would technically be this whole angle. This whole angle is what you need, right? And so if you find that whole angle, you can find this whole arc, okay? In other words, what you have right now is that you have this and this, right? And you need to find the length of this arc here, okay? And what is the information you have? Well, you just found that the radius from part B was 55.2. So this is E, this is B. So this is 55.2, which means that this is also 55.2, right? And you just found that this angle here, just this angle here, is 54.6. And so the length of the arc that you're trying to find that's in red means that you need this whole angle. And so from here it's pretty standard because Ansel walked in a direction perpendicular to AB. That means that these triangles are like pretty much perfectly the same, okay? And so this angle in red is actually going to be 54.6 plus 54.6 because technically this green angle here is the same one. And so the big angle in red, which is what we want, is going to be 54.6 plus 54.6. So the angle in red is 109.2. Okay, now we're getting somewhere. So now I can erase this stuff in green. this whole thing in red is 109.2, right? And so if this whole thing in red is 109.2, now I can pretty much plug in length of an arc. So length of an arc we said was theta divided by 360 times 2 pi r. So from here you can plug in theta, which is going to be 109.2 divided by 360 times 2 times pi times r, which we said was this guy here, 55.2, right? Now you might be thinking, why is he not plugging in pi? And I'm saying, I'm not plugging in pi because technically pi, your calculator has it. Okay, you can plug in pi by pressing this blue button here on top of this, okay? And so you can press second, this button here, you hit pi, okay? And pi is just a really long number, see? I'm not gonna get into why pi exists, but it has to do with circles, okay? Anyways, from here you can say, you can plug all of this in, okay? So you can plug all of this in saying alpha y equals, pop out a fraction, just to make it easier to plug in stuff. So 109 divided by 360 times 2 times pi times 55.2. Bada bim, bada boom, the length of the arc is going to be 105.205 is what we got, right? And if you count three significant figures, you count 1, 2, 3. Do you round it up or keep it the same? You keep it the same. And so for part C, therefore, we have an arc length of 105 meters. Okay, so that is for part C. Later on, they tell us that the outer edge of the track from C to D is also a circular arc with center E, such that the track is 4 meters wide. Now careful, what we just found, right, was the arc that I put in red. And technically in this exercise, you also have like the outer arc, right? And then here you have your track, here's the outer arc, here you have your track. Okay, sure. And so what they're telling you is that, okay, this is 4 meters wide. So from here to here is 4. From here to here is 4. From here to here is 4. Okay, and it also has center E. And we calculate the area of this curved portion of the track. A, B, C, D, E. Sorry. A, B, C, D, E, F, G. A, B, D, C. So let's go back to the original diagram because it's what has the most information. So technically, they want to find the arc that is A, they told us, A, B, D, C. So it's going to be all of this, okay? Okay, clearly that was some terrible drawing, but you want to get the area of this, 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 and this. So they're looking for this shape here, everything that's in white. And what do they tell you is that the distances from here to here are all 4, okay? And so this is a big hint for what's coming. Let's establish how we can solve it, okay? And so for finding the area of this particular shape, it's pretty hard. It's definitely not in your formula booklet. Like, yo, if there's ever a scenario where my friend Ansel wants to find the arc and the sector, and dude, you're not gonna find that, okay? But what you are gonna find is that for circles, okay, you have two main tools in terms of area and length and blah blah blah. So you have length of arc and area of sector. So let me talk a little bit about the difference between the two. So let's say you have this example here. Let's say you have, I don't know, this is R, and this is your angle theta. See? If you were, oh, and this is going to be like a triangle that goes like that, okay? So if you were to use length of an arc, which I will put now in green, length of an arc gives you this. Well, area of a sector, which I'm going to put in pink, so area of a sector, notice it's area, so area of a sector would literally be all of this. So these are your main tools. So area of sector gives you like the whole thing, right? And so technically in this exercise, what we can do is that we can find the area of a sector. We can first find this area of a sector, which I will put in pink. So we can find this area of a sector. Then we can find this area of a sector that I'm putting in green. So all of this okay, which also covers the pink, right? And from here, if you do the green, which is the bigger one, minus the one that I put in pink, you're going to end up with exactly, this is A, this is D, this is B, this is C. You're going to end up with the small sort of sliver at the end of A, D, B, C. Okay, so you're taking the area of a sector twice, first the big one, then the small one, subtracting both, and clearly you need to end up with only what is in here. Okay, you end up with only this, which is exactly what they're asking for. So that is the game plan. So for the big sector in green, right? So for the big sector in green, they tell you that all along it, you have a length of 4. So here, you have a length of 4, including at the very edge. So technically, this distance here, which is the radius of the bigger one, is going to be 55.2 plus 4. So the radius of this big circle, right? So the radius of this big circle is going to be 55.2 plus 4. It's going to be 59 point, oops, that is 49, lol. It's going to be 59.2, while the radius of this smaller one is our classic 55.2. Now, because they are the same arc, just that one of them is bigger than the other, right? The angle that we're going to be using is the same. 109.2 and 109.2. All right, guys, I know this is a little bit confusing, but this is probably as clear as I can get, okay? So, point is, from here, the area of the green one, right? Remembering our equation up here, or actually, for area of sector, you have this. So for area of sector, let me put it here, area sector is theta divided by 360 times pi r squared. Pi r squared. And so for the area of the green one, so area green is going to be the 109.2 divided by 360 times pi times r squared. So 59.2 squared. Minus, and now I'm going to be putting the guy in pink. The guy in pink is going to be 109.2 divided by 360 times pi times r, which is 55.2 squared. And this will equal the area of the thing I'm trying to find. So just to be mega clear, this in green is the sector of the big one, right? And this in pink is the sector of the smaller one. And so if you take the big sector subtracted by the small sector, you end up with the small sliver that you need, right? Of ADBC, okay? So once you do all of that, you end up with, well, look at me spend some time in my calculator. You can just be very careful with how you do this, right? So I suggest using a lot of parentheses here. So this first big parentheses is going to be the stuff in green. So I'm going to have 109.2 divided by 360 times pi times 59.2 squared. So I close this first big parentheses, and this big parentheses is being subtracted by my next big parentheses, which is the guy in pink. So for the guy in pink, I said it was 109.2 divided by 360 times pi times the slightly smaller radius, 55.2 squared. I close all of it. I double check that the parentheses look okay, that the squared also looks okay. Looks all good to me. I press enter, and this is what I get. And so the area of this thing is 436.069. If you want to do 3 significant figures, you count 1, 2, 3, round it up or keep it the same, you keep it the same. So the area for part D is simply going to be 436 meters. Because it's area, it's going to be squared. Okay, so if it's area, so area is going to be meters squared, volume is going to be meters cubed, and distance is going to be meters to the power of 1, which is the same as just leaving it as meters, okay? So area is going to be squared, volume is going to be to the power of 3, distance is to the power of 1. Careful with that, it's part of how you put your answer. Then they tell us that the base of the track will be made of concrete that is 15 centimeters deep. And so, for part E, we need to calculate the volume of the concrete needed to create the curved portion of the track. So if I get very, very fancy with my math drawing skills, you have A, you have D, you have B, and you have C, right? And so technically right now they're telling us, okay, we need to put some concrete on like below this whole part. So if they put some concrete below on all of this, you need to find the volume that fills up like the inside. You know what I mean? And so you need to find the volume of everything that is right below this track, right? So from here you have B, there you have C, right? So you find the volume that fills up this track, right? And so this has more to do with understanding how calculating volume in general works, okay? So for example, if you have a cube that looks something like this, for finding the volume of this, all you're really doing, or how volume is created in the first place, technically this cube is a bunch of these squares that I drew at the beginning, like infinite amount of times, okay? And so technically, if you add, this is the thing, if you add the area of all of these different squares, you end up with the volume of the cube. And so in this case, technically, if you add a bunch of different tracks that go all the way down, so you add a bunch of different tracks that go all the way down, like layering themselves, eventually, if you add all of those up, you end up with the volume, okay? That is how volume is created. You're taking like one shape and multiplying it like a bunch of times and adding all of that together, and that is what gives you volume, okay? So it's this one shape like infinite amount of times, okay? And all of that added together is what gives you volume. And so in this case, you want to take this shape and, sorry about that, you want to take this shape and how many times do you want to like sort of multiply it or whatever? Well, you need it to be 15 centimeters deep. So technically you can take your answer from part D, the 436, and just multiply it, right? So this is meters squared, and multiply it by 15 centimeters. And that's going to give you the volume, because basically you're saying this shape here, this shape here, I need it to be 15 centimeters deep, sorry. And so how many times is it going below? Like 15 times in terms of centimeters. But here, it's not so easy, right? This is worth 3 points. So there's gotta be something fishy going on. And the fishy thing going on is that for part D, you said that the area of the shape that's in orange, right? The ABDC, this guy on top, right? So the shape of this guy, the area of this guy is 436 meters squared. And you want to find the volume when you multiply by 15 centimeters. Uh-huh. So that's a problem. You either go with meters or you go with centimeters. And so I'm just going to show both. See, so on the one hand, you can go the version of meters, right? So the version of meters is making sure everything is in meters. And so in 1 meter, you have 100 centimeters, okay? So that means, notice, from here to here, I had to divide by 100. So, interesting. So 100 divided by 100 gives you 1. So 100 centimeters is for 1 meter. So you can also make this sort of relationship. Okay, so if you're trying to find 15 centimeters, how many meters would that be? Now the relationship is still divided by 100. So you need to do 15 divided by 100, 0.15. And so to leave it all in meters, it would be 436 times 0.15. That will give you the volume in meters. And so the volume in meters would be 436 times 0.15, 65.4. So 65.4 meters cubed would be one way to answer this question. And so there is a world where you leave your answer in centimeters. It's just a little bit more confusing to my sort of intuition, because then with meters you end up with smaller numbers. It's easier to manage. So I suggest that you convert it to meters and you go from there. Okay? There is an answer to do it in centimeters. I'm just going to show you meters because I think it's friendlier. And that would be actually for number 2.